A very quick recall of yesterday's lecture. So we started with the discussion on character equation to derive that, to enforce continuity on the U star and V star fields that we have obtained from the predictor step. So what we did was we obtained we compared the original U and V equations, which are the ones which are discretized at the n plus 1th pressure, and that result in n plus 1th velocities, and the predictor equations, which are discretized at the P star pressure, which is some guess pressure field, resulting in U star velocity fields. Um, and instead, we worked with um discretized form, fully discretized forms, not the semi-discretized forms. So when we do that, we get equations number 1 prime and 2 prime, which are the equations for, equations 1 tilde and 2 tilde, which are the equations for u prime and v prime. That's what we want, because once we have equations for u prime and v prime, they can be substituted into the continuity equation to get the equation for p prime. There's one assumption that we took where we neglected the neighborhood terms containing u prime and v prime in equations 1 tilde and 2 tilde respectively, and that resulted in 1 double prime and 2 double prime. Now this assumption is something that we'll have to see what effect it has on the intermediate steps and the final result. Now for the final result, we discussed that if our velocity u star, it somehow reaches un plus 1, and v star gets corrected to vn plus 1. So if we are able to obtain un plus 1 and vn plus 1 somehow, let's say, then if we use those velocities as u stars, let's say, and then proceed further, then there's nothing to correct, because we already have obtained un plus 1 and vn plus 1. So they are final. So the u primes and v primes for them will be 0, right? So if u prime and v prime for the final velocities obtained are 0, that means that neglecting this term will not have any effect, because ultimately that is going to be 0. So ultimately this assumption is going to hold fine. In the intermediate steps, when our u primes and v primes are non-zero, then neglecting this will not be perfect, in the sense that the u primes and v primes you get by neglecting this term will not be the same as what you would have got if you had not neglected it. Right? So we have to somehow figure out how to take this assumption in the context of what we are doing to, the u prime and v prime that we'll get now after neglecting this will not be the same as what we should have got. So we'll have to do something about it. So we'll discuss that a bit from now. So when we neglect this, we get 1 double prime and 2 double prime. And these are the expressions that we can now substitute. In fact, we call them equation number 3, because we are dealing with staggered grid. So for the continuity equation, you have 4 faces, and each face contributes a different velocity field. Because on the east face, you have an east u I plus half comma j. On the west face of the nominal cell, you have u I minus half comma j, and so on. On the north and south, you have v velocities. So we get this equations 3, which are the equations we'll have to substitute in the continuity equation. And in the continuity equation, which is given as the one at the bottom of the page, it has un plus 1 and vn plus 1. So we write un plus 1 as u star plus u prime, because that's the definition of u prime. So once we do that, then we get this equation number 4, which is the equation for the unknown the u primes and v primes written on the left, and the u stars written on the right. So u stars and v stars are known from the predictor step, so they are already known, and u prime and v prime are not known. So we are going to calculate them, not directly but in terms of p prime. So that's where we stopped, and we'll continue from there. So if we substitute equation 3, which is this set of equations that link our u primes and v primes with p primes, into equation number 4, which is the continuity equation simplified. So when we substitute equation number 3 into equation number 4, we get equation number 5, which is the discretized equation for the pressure correction P prime. So this includes terms P prime ij, which is the I comma j point that you're solving for. But it also has I minus 1, I plus 1, j minus 1 and j plus 1. So it has neighboring points as well. And that is typically what you see in a stencil in pressure Poisson equation. So we'll have to use an iterative method, let's say a Gauss-Seidel method, to solve this equation till convergence. Is that clear? So once we solve equation number 5 using, so let's write that. So using an iterative method, I've written that. So once we have solved this equation, as a result, we'll have the p prime values available at all points in the domain, including boundary points if the boundaries are Neumann or Robin. So then once we have all p primes, now we can correct the velocities and pressures. So next step is to write u. I mean, earlier what we did in simplified marker and cell, we said un plus 1 is u star plus u prime, and u prime was, let's say we are talking about I plus half comma j. So this is di plus half comma j in that notation that we've been talking about, p prime ij minus p prime. Similarly, we'll have vn plus 1 is equal to v star plus something like this, and then we have pn plus 1 is equal to p star plus p prime directly. Indices you can put yourself. But there's a difference here. Have we actually got un plus 1, vn plus 1 and pn plus 1? Why not? Right, so we predicted, like, let's compare this with the semi-explicit scheme that we have talked, SMAC scheme. So there we predicted velocities and we used gas pressure, Pn. And then we corrected, we used the equations at the n plus 1th time, or the original equations, subtracted the predictor equations from there, and we got equations for pressure correction. Velocity correction, and from velocity correction we substitute that into the continuity equation, and we got u prime and v prime, p prime equation. We solved p prime, and from there we got u prime, and from there we got un plus 1 and vn plus 1. So what is different here this time? There is something that prevents us from getting un plus 1, vn plus 1 and pn plus 1 at this step. Let's go back here. Now this was the actual expression for u prime and v prime that we had got by taking a difference of the original equations and the predictor equations. So had we retained this expression to get the pressure Poisson equation in the discretized form and solved it, that would have given us un plus 1 and vn plus 1 and pn plus 1. But we took an assumption. And the assumption was that we neglected the neighboring terms on the right hand side. So if you neglect a term, you will not get the correct values of u prime and v prime. Because see, at the first step, u prime and v prime are not 0. They are something, right? So in the first step, where u prime and v prime are not 0, then the sum over the neighboring points of those values which are non-zero should also not be 0. So if you are removing some finite quantity on the right hand side, the left hand side will not be correct. Agreed? So what we actually get is not un plus 1 and vn plus 1 for the reasons. So I'll write it here. So this is not true, as we neglected the sum over the neighboring terms in the expression for u prime and v prime. Let's see if we have a number for those equations. That's 1 tilde and 2 tilde. But we did hope that we moved in the right direction, in the sense that showing graphically. So let's say this is our un plus 1 and this is our un, right? And if we did not make this, we did not neglect this, so what would happen is that you would get some u star. So I'm drawing it specially, but these don't worry about where the points are. All just think of the how far they are from the actual un plus 1. So I'm writing this line, which is sort of divergence-free velocity fields, and this I've deviated from the line because now u star that we got from predictor equation did not satisfy continuity, so it's not on the dotted line. So earlier what we did was, when we used this max scheme, then we had a un, we got a u star by solving the predictor equation, and then we corrected it. So step 1 and corrector corrector step was step 2. But here what happened was, so this was the SMAC scheme. Here what happened was that we got a u star after predictor step, but since we did not correct it properly, because of this assumption that we have, it was not able to reach. It did reach the dotted line, because the fields that we get are definitely divergence free, but we reach here. So we are towards un plus 1, but not there yet. So we still cannot call this intermediate velocity as un plus 1. So we still call it we call it u star. But u star, which is the next iteration. And now we'll proceed with the same step again. We'll predict and we'll correct. We'll predict and get there. It's a very important idea. I mean, that's linked with these terms that we neglected. Are there any questions regarding this? Good point. To make our life easier, try this. Just keep them and then try to formulate the Poisson equation. See what you get. Life becomes very difficult. See these u primes and v primes that we have. I mean, right now what we did was we simply substituted the expression for this u prime into the equation. So here, right? So equation number 4 had u primes and v primes. We simply substituted that as some d into a difference of pressure, p primes. But if you had the retained those points, you would have got the neighboring points. So it sort of becomes messy. In fact, it becomes, u prime depends on neighboring points. Neighboring points now depends on their own neighboring points, and so on and so on. And it becomes a very dense system which contains all the points. One equation contains all the points. Okay. So we want a sparse system in the sense that the stencil should be small. In CFD, that's what you want. You want the stencil to be small, because each equation will have then 5 points contributing to it, and then we can solve it using iterative method. But if you write the equation for one point which contains 4 points, but these 4 points now contains their 4 points, and then so on and so on, then each equation has all the points. Imagine the amount of computational work you have to do. It's much easier if you do this small amount of work many times rather than doing that large amount of work once, which actually is almost impossible. Okay, we do this to make our life easier computationally. But then the good thing is that I mean, without any proof, I've shown you that we do get there ultimately, closer and closer. It's a very important idea. Okay, so this was not true. So I'll just put a red with a cross so that you don't get confused. This is not the case. So what we have is, when I correct u star plus the difference in pressure. So this is basically, we have reached here now at this u star, intermediate u star. But this u star, the new u star we have obtained, will satisfy continuity because it's on that dashed line. It's been corrected. So this we'll call a u star again. Okay. We could have called it something else, but let's because we don't need the old u star anymore. So we are sort of replacing the old u star with this new u star, which satisfies continuity. Okay. Then you will go to another u star which does not satisfy continuity, which is from this u star that I've circled to this u star that I've squared by solving the Pareto equation. And then you will again obtain a new circled u star which satisfies continuity. So we have to move on this dashed line, but for that we have to zigzag through the predictor equations. So essentially what continuity is doing, what corrector equation is doing for us here is to help us move on the dashed line, help us keep on the dashed line. Okay. Any questions? So the pressure also we cannot call Pn plus 1. If pressure was Pn plus 1, and then velocities will also be, whether they're linked to each other, right? So we also call this a new P star. So once we have these divergence-free U stars and V stars, which we obtained in the step above, the next thing is to go back to equations 1a and 2a, which were our predictor equations. And then we repeat the whole process. And we do it many times until our P star approaches Pn plus 1, and therefore U star and V star approach Un plus 1 and Vn plus 1 respectively. So there are lots of loops in this case. So this is one loop because you have to repeat this, and there will be a test to come out of the loop that when our U star will stop changing, because if U star has become Un plus 1, then the U primes will be 0, right? So if U primes are 0, then U star will not change anymore. It will be the same. It's like you have reached the end point or very close to the end point, and there is no further, that this distance between these U star that you have obtained on the dashed line and Un plus 1 is epsilon. So any improvement you make will be less than epsilon, right? So you have converged. This is one. And there was one loop that was inside the predictor step, because predictor step was implicit. So we are using Gauss-Seidel to solve the U stars and V star in the 1a and 2a equations. And there is one loop in the P prime equation, the Poisson equation. So lots of loops. So good news for you is that we are not implementing this in a program in this course. But I would definitely urge you to try that as an exercise in your vacations. So once convergence is achieved, we get Un plus 1 is your U star and Vn plus 1 is your V star, because you are storing U star and V star. So once you have achieved convergence, you will say that the final U star you have stopped at is your Un plus 1. Similarly, so you have done all this work to get the velocities and pressures at the next time step. We started with Un, Vn and Pn, and we have finally obtained Un plus 1, Vn plus 1 and Pn plus 1. So that's one time step completed. But you would typically need many time steps. Or if you are going to steady state, you will keep on repeating the time steps until the difference between Un and Un plus 1 is negligible. It's less than an epsilon. Okay. So then we call it n equals n plus 1. That basically means that your new Un value is Un plus 1, because now you have to compute the next time step values. So whatever you have obtained now, they are put into the nth time values. So we already have discussed this, but I would want to write this for those who are going to read the notes. So why does the scheme give the correct solution, that is un plus 1 and vn plus 1, even if we neglected the sum over the neighboring terms in the velocity correction expression? And the answer is that because we know that we are moving on the dashed line and approaching towards un plus 1. So when we have approached very close to un plus 1, that is when our u star is equal, let's say equal to, but equal to in the sense of sometimes we write this as equal to with an epsilon on the top. So that would mean that it's extremely close. It means that u star minus un plus 1 mod is less than epsilon. Okay. So when u star is very close to un plus 1, then your u prime is close to 0. Because if your u star is equal to un plus 1, then when you take the difference of the equations 1 and 1a, there's nothing there, right? Because u prime is defined as the difference between u star and un plus 1, but they are equal. So u prime is 0. So if u prime is 0, this implies that the sum over the neighboring terms expression is actually 0. So whatever we neglected ultimately has no contribution to u prime. But that only happens, it only becomes true if your u prime actually is 0. Close to 0. How do you judge that P star has converged to Pn plus 1? So what will be P prime when P star has converged to Pn plus 1? 0, right? So let's go to this equation number 5. Well, sorry, let's go to, let's look at equation number 4 for the expression of D star. So, because D star is something we are calculating. You need D star for solving equation number 5. It's a right hand side. And D star is in terms of U stars and V stars. So what is D star when all the P primes are 0? Look at equation number 5. 0, right? So you are calculating D star using U stars and V stars, which are non-zero, but their combination will give a 0. So what you do is you can put a check on D star. So you can say that if my D star is 0 or equal to epsilon 0, that is close to 0, that means you have converged. So rather than checking for other things, you can easily check for D star. And if D star is close to 0, you're done. Okay. So that's a good way to check, because D star is something that's already being calculated before solving equation number 5. You need the right hand side. So you just check that. If it is 0, then there's no point solving it. So you're done. Right, so we're done with this algorithm. So let's write the algorithm in a nice way so that when you have to implement it, um, whenever if you have to implement this, it's easier to understand the overall flow. And then I'll make a minor change to it and show you how you can modify the algorithm to solve the fully implicit form. Till now, we are solving the semi-implicit form, which uses the flux at the nth times for the reason that we have discussed. But we can now modify this to solve a fully implicit form, and that is what ultimately you'll want to solve, fully implicit form. So let's write the algorithm and then discuss it, and then we'll be done. So this method that we have discussed is called simple semi-implicit method for pressure linked equations. I'm sure you have seen this simple method in ANSYS. When we are deciding on the solver, we saw that simple was there. And if you look at the open form help, there also the solver is available. So typically, solvers have the same ideas. There could be minor changes on how they implement an idea, but more or less they are going to have a predictor corrector step, because you don't have the actual pressure, so you have to guess a pressure, and then from there you get U stars and V stars which do not satisfy continuity, and then you have to solve a corrector step using enforcing the continuity to get divergence free U stars and V stars, which then you have to keep iterating until you reach UN plus 1 and Bn plus 1. So all the methods will typically have the same idea, except that there will be minor differences. But if you understand this, then you can understand any method in CFD for solving complete fluid flow equations. So let's write the algorithm. So on the left we have step numbers. So we initialize delta x, delta y, delta t, etc. And then you need the values of u, v, w. Now this method can be expanded to 3 dimensions also, although we discussed for 2D, but there was nothing keeping us in 2D. All we have to keep writing is a third equation for w, and draw a cell which looks 3-dimensional in shape. So we have to initialize the u, v and w values at n equal to 0, and so is the pressure value. We just have to make sure that the values of u, v and w that we initialize are divergence free. Okay, and this discussion has we had it in the SMAC method, so I'll not repeat it. So I'll just write C discussion on SMAC. So we spend a good amount of time to figure out how to get these initial velocities which are divergence free, and the pressure is also compatible. Now if you're solving a steady state problem, then the initial conditions can be arbitrary. You can choose velocities equal to 0 as long as they satisfy this divergence free criteria. You can have arbitrary initial conditions for steady state. But if your initial conditions are closer to the steady state solution from your intuition, then you will need lesser amount of computational work. Arbitrary in the sense of not linked to any particular solution at any particular time, but they cannot be completely arbitrary. They have to satisfy this divergence free velocity field and compatible pressure field. So next is to find the mass flux capital F at the nth time at all the phases, because we need this in our predictor equation. And we also need a P star in our guess pressure in our predictor equations. So we can take P star equal to Pn as the first guess. But subsequently you will be getting new P stars and you can use them. Okay, so once we have obtained a P star, and once we have Fn and flux and P star, we can solve equations 1a and 2a iteratively, of course, and we solve them till convergence until we get the U stars and V stars which satisfy these equations with the assumed P star value. So RHS of pressure correction equation is nothing but D star Ij. So we compute the RHS of pressure correction using U stars and V stars. Next, we solve equation number 5 using iterative method. That's a pressure Poisson equation, and we solve it until we have obtained the solution to that equation. Again, we'll use an iterative method like Gauss-Seidel method to solve it because um, it's containing nearby points. So once we have solved the corrector equation, then we update our U star, V star and P star. Now they are still starred values, not uh, n plus 1th values, because of that assumption that we have taken of neglecting the neighborhood terms. So we are moving on the dashed line towards final un plus 1, vn plus 1 and pn plus 1. Now, once we have done this, we have to repeat the predictor step. So we'll say go back to step number 3. So what was step number 3? That was where we solved the equations 1a and 2a. So we'll repeat this. So once we have achieved the n plus 1th time values, then we say that un plus 1 is actually equal to the u star value I have obtained, vn plus 1 is equal to the v star value I have obtained, and pn plus 1 is equal to the p star value that I've obtained. And then this is one time step completed. And next we say n equals n plus 1. And then we go to step number 2. So step number 2 was the step where now we have to find the fluxes again, and then we have to basically repeat the whole process for the next time step. So let's summarize this into a loop structure. So we have a loop for time steps where you keep increasing the value of n and you repeat the work. And inside time step, what we do is we solve first the predictor equation, and then we solve the corrector equation. So while solving the predictor equation, which is equations 1a and 2a, we have to iterate to solve the predictor equation, right? Because we are using a Gauss-Seidel method for solving u stars and v stars in 1a and 2a. So there is what we call a predictor loop to solve these u stars and v stars using iterative method. And then if you look at the equation number 5, which is step number 5 here, which says iterate equation 5 to convergence. Equation 5 was a pressure correction equation. So again, that is also inside a loop. So with that we call a corrector loop. Okay. But that's not it. Now this predictor corrector combined step is done many times. Because when we do it once, we are not able to reach Pn plus 1, Un plus 1 and Vn plus 1. So we do it many times. So there is actually a loop here that we'll call the, to give it a name, let's call it convergence to n plus 1 loop. Okay. Moving on the dashed line. So we are converging to n plus 1th values. So there is one time step loop, one convergence to n plus 1th loop, one predictor loop, and one corrector loop. There's a big time step loop. Inside that you have many convergence to n plus 1 iterations. And in each convergence to n plus 1 iterations, you have many predictor iterations and many corrector iterations. So I think let's stop here, and then on Thursday I will discuss how to solve the fully implicit method. That's only a 5-minute discussion, and then I'll also want to discuss some special topics which did not fall under any particular subtopic that we have discussed. Just for those, especially research students who will be implementing this for their research, they'll greatly benefit from these special topics, hopefully. And then on Saturday's class, which is actually going to be a Monday, we will summarize the whole course. And if you have any questions, I'll be happy to answer.